Welcome back, everyone. In this video, we'll continue talking about default-adjusted expected bond returns. There's a mini exercise associated with this video, which we'll discuss. Let's start by taking a look at the example that we worked through in the previous video, where we had a 2-year bond, right? And then we had a probability of not defaulting in each period, 90% chance. In the notation that we'll be using, that probability of not defaulting, the probability of making the contractually obligated coupon and face amount payments, is pi. So pi was 0.9 in our first example, right? And then in the event of default, if the firm defaulted, 10% chance in each period, we assume that bondholders just got nothing. Like we talked about previously, though, when a firm defaults on its bonds or even goes bankrupt, bondholders usually get some amount back. And so that's denoted by lambda in our model. So we're going to work lambda into our default adjusted bond expected return model in this video. So let's see how it looks. Right? We'll go back, we'll take a look at just a 1-year bond. So there's just, when the bond matures, there'll just be a coupon payment and the face amount, right? And if the bond doesn't default, that's the cash flow a bondholder would receive after 1 year. So the coupon rate is Q, annual coupon rate. The face amount is F. So the coupon payment is Q times F. Right? So this is the amount of a coupon payment. This is the face amount. These are the two cash flows we would receive when the bond matures, just like here in year 2 of this bond from the previous video. And then that happens if the bond does not default. And so the probability of that taking place is pi. And then there's a 1 minus pi probability that the bond defaults in this model, in which case when the bond defaults, we get some fraction of the face amount, where that fraction, that portion is denoted by lambda. So let's work through an example on the next page about this. And I went ahead and wrote out the formulas that we'll work with to find the expected cash flow. So this bond matures in 1 year. It's got a coupon rate of 8% and a face amount of 1,000. So an annual coupon payment from this bond would be $80, right? And then we've got a probability of not defaulting, pi, and then a recovery rate in the event of default. So let's plug things in and work through it. And then this is going to form one building block for a much bigger default adjusted expected bond return model that we'll look at in the next video. So we've got a 90% chance of receiving the cash flows in the event of no default, right? 90% chance of receiving coupon rate times the face amount, $80, plus the face amount. There's a 90% chance of that. And then there's a 1 minus pi chance of receiving the recovery amount, lambda, 40% is the assumption, times the face amount. So in the event of default, we're assuming that bondholders get about 40 cents on the dollar in terms of face amount. So this math comes out to 0.9 times 1,080 is 972. Plus 0.1 times 400 is 40, right? And so the expected cash flow from this bond is $1,012 based on the probabilities of these cash flows happening, right? And so that's the expected cash flow, and the expected return is just a function of in this bond, our default adjusted expected return for this bond. You can see this numerator is just the expected cash flow as a fraction of the price, right? So if we expect to receive $1,012 from this bond, and then the price we're paying for it, P, we pay $975, we're expecting to receive $1,012. That math comes out to be 0.0379 or 3.79%. 79%. Great. So this is how we'll compute default adjusted expected bond returns. But we're actually going to look at a little bit more involved model in the next video. And before we close out, let's set it up because, for most bonds, it's not that they just either do or do not default with the same probability every period. Like a bond usually starts out with one credit rating, and as things go better or worse for that bond over time, the rating agency might reduce the credit rating, right, to reflect the increased default risk. And then I suppose if an issuer's credit quality gets stronger over time, a rating agency might raise a bond's credit rating to reflect reduced default risk. So we're going to look at a model where a firm has a bond has a certain credit rating, right, as a starting point, and there's a probability of the rating either increasing or decreasing. And once the rating gets to a certain level, there's a probability of default. Because in real life, almost no bonds go from like a really high credit rating, like AA, all the way down to default immediately. Usually there's a ratings downgrade along the way. So that's called a Markov model, where there's a probability of switching across, from one state to another as time goes by. There's probability of starting at a high rating and moving to a lower rating, probability of going from a low to a high, probability of going lower to default. And so this model we'll look at will have really two ratings where a firm isn't bankrupt, A and B, kind of a simplification. And then there's also two states where either the bond is defaulting in the current period, right, in which case bondholders receive the recovery amount. And then if we're looking at a multi-period model, there's this fourth rating E that we'll look at, this fourth state that denotes that a bond has defaulted already, so there's no cash flow right now. So the mini exercise is related to recovery rates and then also credit ratings. So what I'd like you to do is find some data or a news article on either default probabilities by credit rating, right? If you can find more current data on default probabilities by credit rating, that'd be great. This table is 10 years old, so I'm wondering if it's changed over time. Or if you can find a Wall Street Journal article on recovery rates or bond defaults, that's the mini exercise. All right. So in the next video, we'll get into this Markov model and compute a default adjusted expected bond returns across multiple ratings and across multiple years. And it involves, you guessed it, matrix operations. So I look forward to talking with you about it in the next video. Thanks for tuning in.